Let's start a new topic, vector functions of a scalar variable. This is the definition of differentiation of a vector function. Suppose V is a vector depending on the scalar alpha. That means for different values of the scalar alpha, we have different vectors V. So this is not necessarily a constant vector. And as such, it's a function of that alpha. Because the values of this function are vectors, it's a vector function of the scalar variable alpha. Then the derivative of this function with respect to its independent variable alpha. You see, the function is a vector function, but the independent variable is a scalar. And the derivative of the function with respect to that alpha is defined by this limit in the usual way, just like how we define derivatives of ordinary scalar valued functions. Limit as delta alpha tends to 0 of v of alpha plus delta alpha minus v of alpha divided by delta alpha, provided of course that the limit exists. If it exists, then we say that this is the derivative of this function with respect to alpha. Now let's look a bit more carefully at what this actually means. Let's forget about this limit for a moment. Let's look at this ratio. It looks like a ratio, so I am calling it a ratio. What do you see in the numerator? This is v of alpha plus delta alpha. That is a vector from which you are subtracting this vector v of alpha. That means the difference is a vector which you are dividing by this scalar delta alpha. That means this is ultimately a vector. Note one more thing, that because we are considering this limit, delta alpha is approaching 0 but it's never equal to 0. Okay, so as delta alpha changes, this vector also likely changes. That means this is a function of delta alpha. For a given chosen alpha, alpha does not change, but here delta alpha is changing and it's approaching 0 from both sides. Okay, this is a two-sided limit. But then, what does that mean? What does it actually mean for a vector function to have a limit? And whenever such a limit exists, what is that limit? What type of mathematical object is that limit? And the answer is that that is also a vector. What did I say here just now? That if we forget the limit for a moment, this thing is a vector and it's actually a vector function of the variable delta alpha. I am not talking about this v, okay, this entire thing. Let me call it capital V. So capital V is the vector function of this delta alpha. For that chosen alpha, the only thing that changes is delta alpha. So as such, this ratio becomes this vector function of that variable delta alpha, whose limit, if it exists, will also be a vector. However, still more questions arise. What exactly is the meaning of this limit? This is the meaning. For every epsilon greater than 0, there is a delta greater than 0. These are real numbers, of course, such that if these inequalities are true, then this inequality is also true. These inequalities say that if the distance between the real number delta alpha and 0, which is this absolute value, is greater than 0, that means it's not equal to 0. This ensures that delta alpha itself is not equal to 0. And if this distance is less than delta, then this thing is less than epsilon. Note that this means that if delta alpha is close to 0 in the sense that it is less than that delta. What is the meaning of this left hand side of this inequality? Here you are looking at the difference of two vectors. So that means this is a vector and this is not absolute value, this is magnitude. And magnitude, as you know, is a real number. So that is why this inequality makes sense. So in this sense, if this happens, then we say that the vector function v of delta alpha has this vector as its limit when delta alpha approaches 0, and your v of delta alpha is this. That is why this is a vector, just like v itself is a vector. All these things were happening keeping alpha fixed, however alpha can be any alpha. So if you now vary alpha, you get another vector function of that same scalar variable alpha, and that vector function is in fact called the derivative of v with respect to alpha. If you evaluate this vector function at different alphas, in other words, if you change this alpha, then you will get different limits. All of them may not exist, I mean those that exist give us the different values of this vector function. All those values are vectors, and that is the derivative of v alpha with respect to alpha. There are rules for differentiating vector functions, just like we have rules for differentiating ordinary real valued functions, and these are similar. Let u of alpha and v of alpha be vector functions of the scalar variable alpha, and let lambda of alpha be an ordinary function, that means a real valued function of alpha. Then the first rule is this, which is exactly like what you have for real valued functions. The sum of u and v will be differentiable. We did not really write everything here because you are already familiar with the similar rule for real valued functions from calculus. Actually, this should have been written. I mean, if we want to write it in detail, if u of alpha and v of alpha are differentiable at alpha, that means if both of them have derivatives at alpha, then their sum is also differentiable at alpha, and the derivative of the sum is the sum of their derivatives at that alpha. But instead we just have written this equation, or rather the author has written this equation. Next, number 2, if the ordinary function lambda of alpha and u of alpha are both differentiable at alpha, then this scalar multiple of the vector function u by the scalar function lambda alpha is also differentiable at alpha, and its derivative is given by this. So this is like your product rule. You differentiate lambda, and with that you multiply this vector, keeping the vector as it is. That is one term, plus then in the other term you keep lambda as it is and differentiate the vector function. The next one involves the scalar product of u and v. If u and v are both differentiable at alpha, then their scalar product, which then becomes an ordinary function, ordinary means a real valued function of alpha, is also differentiable at alpha, and its derivative again is given by this expression, which is just like that one. The only difference is that now in place of lambda you have this vector function u, and there is scalar product. Okay, so that scalar product persists and the other things are similar. That means the form is the same. You differentiate u, and with that you take the scalar product of v, and in the other term you take u, and with that you take the scalar product of the derivative of v. And finally we have one more, which involves again u and v, but this time they are vector product. And the form is same. The only difference is that here we have scalar product, here you have vector product. That's just it. But of course, this makes sense only when both u and v are differentiable at alpha. So that those things are there in the background. Now the author, in spite of saying that in this vector calculus part he would provide us with all the details, has not actually given proofs of these things. I am also not going to do proofs here. If you want proof, you can either see in any vector calculus book or you write in the comment section below. Because proving these things really is not our aim. We want to be able to use these things to see what we can do in mechanics. Now, why do we need differentiation of vector functions of scalar variables? That is because we are soon going to define the velocity and acceleration of a particle that is moving in a three-dimensional space. To interpret those things, and actually not just interpret, to even define these things, we are going to need differentiation of vector functions. That is why, because both velocity and acceleration will be vector functions of a scalar variable, and that variable is time. So let's now see an example. Example 110, where we are going to apply these ideas. There are two parts. This is part 1. The position vector of a particle P at time t is given by r. What I was saying just now. So this just means that there is some particle which is moving in three-dimensional space in some way. In what way, that is actually given by this function. There is a reference frame, there is an origin somewhere. With respect to that origin and with respect to that reference frame, we are observing the position vector of that particle. What is that position vector? That position vector has its initial point at the origin, and the terminal point is at the particle. As the particle moves in three-dimensional space in some manner, that vector changes. Possibly both its magnitude as well as direction change with time, and that vector is this vector r. Ideally, the author should have written r of t, indicating that r is a function of time, but that's understood. Sometimes we just simply write r. If anyway it's given that it's the function of time. What function? 2t squared minus 5t I hat plus 4t plus 2j hat plus t cube k hat, where this I hat, j hat and k hat form an orthonormal basis set. Okay, but what is more important is that it is constant. Constant with respect to what? With respect to time. This is your frame of reference. And the point from where these vectors are emanating, I hat, j hat and k hat, is that origin with respect to which we are measuring this position vector of the moving particle. So if you put some particular value of time, then you get the location of the particle by seeing the tip of that position vector at that time instant. And now what is it that we have to do? We have to find the derivative of r with respect to t and the derivative of the derivative, that is the second derivative of r with respect to t. You probably already know that this is the velocity of the particle and this is the acceleration of the particle. But we will see those things afterwards. Okay. Although we are going to calculate velocity and acceleration, but right now we are not using those words. We just simply calculate these quantities mathematically, and let's see what we get. So we first calculate dr dt, and to do that we apply the first differentiation rule, where we have a sum of two vector functions. Because our original vector r is a sum of three vector functions actually, you can use the extended version of that rule to write this. That means because r is this plus this plus this, so the derivative gets distributed over the sum. So this is by rule 1. In the next step we have to apply rule 2, because here we see a vector. It's a constant vector. I hat does not change with time, but still you can regard it a function of time which is a constant function, a constant vector function that has been multiplied by a scalar function. So this part is your that lambda alpha, and this is your u alpha. So that is why by rule 2, only this derivative will be this plus this. Here you have differentiated the scalar function, and with that you have multiplied the vector function. Here you have kept the scalar function intact, and with that you multiplied the derivative of the vector function. Now note that because I hat is constant, it does not change with time, so this will be 0. Just like a constant real valued function has 0 derivative, a constant vector valued function also has 0 derivative, which comes from properties of derivatives of vector functions. So that means this part will be 0. What type of 0? Let us also see that. What type of 0 will this be? This will be the 0 vector, because you can only multiply the 0 vector. Well, you can also multiply 0 scalar by 0 scalar, but in this case this will be 0 vector which you multiply by this scalar and you get 0 vector. So that 0 vector, when you add with this vector, you only get this vector. If you somehow think of this part as 0 scalar, then this addition does not make sense. But anyway, this part won't be there. So that means we only differentiate this and we keep I hat just I hat. So now with that understanding, I will simply erase this, and accordingly I will write these things also and complete this step. So that's how we next have the second term, which is derivative of 4t plus 2 times j hat, and plus the third term, derivative of t cube times k hat. And now these are ordinary derivatives which you can calculate using calculus. Differentiating this, you get 4t minus 5, that times I hat plus 4 times j hat plus 3t square times k hat. So this is your dr dt. Note carefully that this is also a function of t, and now we are going to differentiate this once more with respect to t to find the second derivative. Understanding this calculation now, we can do the second derivative quite fast. You differentiate this with respect to t, you get 4. So that's how you are getting 4i hat. 4 is constant, so that contributes 0. When you differentiate it, you get 0. So there is no j component. There is no j. And differentiating 3t squared, you get 6t. So that's how you are getting 6t k hat. So this is your second derivative. And now let's see part 2. Part 2, consider the vector function a, which is a function of the scalar variable t, which is time. And let b be a constant vector which does not change with time. Then this is what we have to show. The derivative of a dot, so what is this? This is triple scalar product of 3 vectors obviously. One of them is a, then the next one is a, but what is this overhead dot? I am coming to that, okay. And the other one, the third one, is that b. That is equal to another triple scalar product, where this time again we have a, but here we have another thing which we have to understand. A with 2 dots overhead times b. So let us first understand what this and this mean. A with 1 dot above just means dA dt, and a with 2 dots above means the second derivative of a with respect to t. Instead of writing these cumbersome notations, you can use these dots. These are Newton's notations and are used when the independent variable is time. Solution. So we start with the left hand side. So this is the derivative of the scalar product of these 2 vectors. So by rule 3, that will be equal to this plus this. That means first you differentiate a, keeping this other thing intact, do not change it. So that way, because you are differentiating with respect to t, by this notation, this is just your a overhead dot. Dot this other thing. Plus then you keep a intact and you differentiate the rest. So this is a triple scalar product where two of the three vectors are equal, and recall that when that happens, it becomes 0. 0 what? 0 scalar. So that means this will vanish and we will be left with this. And then further here we have to differentiate more. To carry out this differentiation, we have to apply rule 4 because we have vector product here. So say you differentiate this vector first, obtaining this A with two dots above it, and the other vector B remains unchanged. Plus then in the next term, you do not change this and you differentiate B. Because B is constant, this is the 0 vector, and the vector product also becomes the 0 vector, so this vanishes and you are left with this. And this is what you wanted to prove, right? Let me end the video here itself. In the next video on mechanics, we are going to see two new things: the unit tangent vector and the unit normal vector to a point in a given space curve. By space curve, we mean that a curve which does not necessarily lie in any plane. It can twist and bend in space in any way.